Okay, so this is question 9. It is an area and volume question, and it goes like this. A cornetto ice cream cone is a branded frozen dessert product created and manufactured in the shape of an inverted right cone. It was first produced in Naples, Italy in 1959, but is now sold widely throughout the world. A researcher is investigating the packaging requirements for different sized cornetto ice cream cones. A standard sized cornetto ice cream cone has a slant height of 16 and a diameter of 6, so there's two crucial bits of information there. And the diagram below shows 3 possible nets for the wrapper of the ice cream cone. Which of the above shows the correct net for the wrapper? And the answer is B. That's a hit or miss question. That is the net for a cone, while the rest are not. Okay, so just B for that. Assuming there is no overlap on the wrapper, collect or calculate the area of the paper required for the wrapper correct to the nearest centimetre squared. So you're going to need the area of this part and the area of this part here, okay? And the formula is an area of a circle and the area of a curved surface area of cone added together. So essentially you're going for pi r squared, which is the area of a circle, added to pi r l, which is the surface area of the cone, okay? So all you gotta do is sum in your values. For the moment we can keep pi as it is, so I'll say pi by the radius. Well, if the diameter is 6, the radius must be 3 squared, plus pi times 3 times the slant height which we were given, which is 16, okay? And this is going to work out as 9 pi plus 48 pi. Add that together and you get 57 pi. And when you multiply 557 by pi, you get in and around 179.070781. 070781. Or in other words, we're asked to calculate the nearest centimetre, so the nearest centimetre is going to be 179. So 179 centimetres squared, because we are calculating the area. Alright? So then it says calculate the value of theta, that's what that sign means, the angle at the base of the net as shown in the diagram above. Give your answer correct to the nearest degree. So the formula you need here, guys, is theta over 360 multiplied by pi r squared. Alright, and that should be equal to the surface area of the cone, so pi is equal to pi or L, okay? So that's what we're essentially looking for here, okay? So this is how you work it out. So sub in your values. Theta over 360 is going to stay the same for the moment. Multiplied by pi r squared, multiplied by pi, multiplied by r squared. The formula you need for this one here is theta divided by 360 multiplied by pi r squared, which is equal to the curved surface area. Now, if you think about this, this is the curved surface area here, okay? Which is what we worked out already, okay? And what we're essentially saying is we need to let, so this is a formula that was given to you in your log tables, okay? And it is, so if you need to find theta, an angle, so if you think about this, this is essentially a sector of a circle that we can't see, okay? Alright, so this, you could turn this into a full circle if you want. So we're going to need this formula here, pi r squared multiplied by theta divided by 360, okay? So there it is there. And I can actually let that equal pi r l, because pi r l we worked out here, which is going to be 48 pi. Okay, and in this case, if you think about it, if this is the slant height and that's 16, then for this formula our radius is actually going to be 16. Okay, so it's going to be multiplied by 16 to be squared, which is equal to pi or L, which we know is 48 pi. You can cancel your pi's, okay, and you get theta divided by 360 multiplied by 256, which is now equal to 48. Okay. So if this side is being multiplied by 256, I'm going to need to divide this. So theta over 360 is going to equal 48 divided by 256. And then we're going to need to multiply. If theta is being divided by 360 here, then theta needs to be, this needs to be multiplied by 360, and so does this. It's going to equal 48 divided by 256 multiplied by 360. Okay. And finally then, just work that out and you end up with 67.5. And you're to round that to the nearest degree, which is 68 degrees. Okay, and that was that question, or that part of question 9. So let's look at part B. Okay, so the part B says the manufacturer wants to investigate the idea of producing a supersized ice cream cone. It is proposed that the standard size ice cream cone would be enlarged by a scale factor of 1.5. Find the slant height and diameter of the supersized cone and hence calculate the area of the paper required for the wrapper, correct to the nearest centimeter squared, assuming there is no overlap on the wrapper. Get started with this question then. What we're going to need to do is we're going to have to multiply the slant height of the original cone's wrapper by the scale factor, and then multiply the diameter of the original cone's wrapper by the scale factor. So start with the slant height. So slant height is going to be, so the slant height was 16, and now we're multiplying that by the scale factor, which is 1.5, which is equal to 24 centimeters. And then the same with diameter. Okay, it's going to equal 6 multiplied by 1.5, which is going to give me 9 centimeters. Okay. And then it's essentially the same question as it was before. So if we go back to this one here, we're going to do this exact thing, exact same question, but this time we're going to use our scale factors, so 24 and 9 instead of what we were using originally. So it's going to be pi r squared plus pi r l, okay, which is going to be pi times the radius, which in this case is going to be 4.5, so it's bracket 4.5 squared plus pi times 4.5 multiplied by the new slant height, which is 24. Okay, and that gives you 20.25 pi plus 108 pi, which is going to equal 128.25 pi. Okay, and then if you multiply that by pi, you end up with 402.909, or in other words, 403. So to the nearest centimeter squared. Okay, and that is the answer to that one there. So part 2 says find the ratio then of the wrapper for the supersized cone to the area of the wrapper for the standard cone. What can you conclude in relation to the ratio from your answer? Okay, so to start this question off, write the two areas down beside each other. So in the last question it was 57 pi as a ratio to 128.25 pi. You might be asking yourself, why am I using the pi values instead of the exact values? Well, I can actually just cancel the pi's there, so I'm left with 57 is to 128.5. I'm going to divide 57 by 57 and I'm left with 1. And if I divide 128.5 by 57, I end up with 2.25. And interestingly enough, that is 1.5 squared. So my conclusion, okay, is that the ratio is 1 is to the scale factor squared. Okay, and that is it as simplified as possible. Okay, and that is the conclusion there. Alright, so the last question then was to do with volume. Okay, so before we can actually do the volume, we have to consider the cone itself. Okay, so you have your cone like this, okay, and we're going to start with the original one, and then on this one is the larger, the supersized cone. Okay, and in this one here, our radius is 4.5, and our slant height was 24. Okay, and over here our radius was 3, and our slant height was 16. What we're looking for first is the height of these cones. Otherwise, we can't find the volume. So if you look at this, there's actually two right-angled triangles there. Okay, so we can actually use Pythagoras Theorem for both of these cones to work out what their height is. Okay, so I'll start with the small cone first. So it's 16 is the hypotenuse here, so that's going to be 3 squared plus the height squared is equal to 16. While over here it's going to be 4.5 squared plus h squared is equal to 24 squared. Okay, so if I get this right here, 16 squared is 256, 3 squared is 9, is h squared there. So h squared is going to equal 256 minus 9. H squared is equal to 247. Therefore, the height is equal to the square root of 247. Okay, so now we need to find the volume then of this cone here, which is a third. This is the formula now. A third. Where's it gone? A third pi r squared h. So in this case, it's going to be a third multiplied by pi multiplied by r squared, which is the radius squared, so I'll just skip chapters and go 9, multiplied by the height, which we have worked out to be the square root of 247. Okay, and when you work that all out, you round it up to 148 centimeters cubed, because this is the volume that we're talking about now. Okay, alright. So over here, I actually just realized, guys, all we have to do is multiply the height here by the scale factor, so we can actually forget about this for the moment. Alright, so it's going to be the square root of 247 multiplied by the scale factor, which is 1.5, and that gives us 23.57435. 57435. Okay, so that's actually the height of the large cone. Alright, so what we're going to do then is just sub it into the same formula, a third pi r squared h, which is going to be a third multiplied by pi multiplied by not 9, it's going to be multiplied by the radius squared, which is 4.5 squared. So I'll just put that in, 4.5 to be squared, multiplied by this number here, which is the height, 23.57435. Okay, now when you multiply that all out, you approximately get 500 centimeters cubed. Okay, so then you have to do the last part, which is the ratio. Okay, kind of running out of space. Ratio then is 148 is to 500. Okay, if you divide 148 by 148, you get 1. If you divide 500 by 148, you get 3.378378. Sudden jump in editing there, guys, because the video on my iPad actually ran out of space while I was recording this. So just a quick recap, we worked out there that the volume was 148 centimeters cubed for the small cone, and the large cone was 500 centimeters cubed. So to finish this question off, we just had to do the ratio. So I put 148 in ratio with 500, divide 148 by 148 and I get 1. Divide 500 by 148 and I get this number here, 3.78378. And the last thing then is, if you actually think about it, that's very close to, or if you find the square root of it, it's 1.500500 all to the power of, to the cubed, right? So it's the scale factor cubed, which kind of makes sense because the area was the scale factor squared, while the volume is going to be the scale factor cubed. Alright? So your conclusion then is the volume of an enlarged cone is the volume of the standard cone multiplied by the scale factor cubed. And that's the conclusion. And that brings you to the end of question 9 of paper 2, which was an area and volume question.